Okay, so it's my pleasure to introduce Eveline Legendre, who is going to give, from the University of Toulouse, who is going to give a talk on relative stability of polarized varieties.
Okay, thank you. Thanks for the invitation. Yes, I will talk about joint work with Rui Dervan, which is in Cambridge, about evaluative stability of polarized varieties. So there's a very nice work by Fujita on many papers that proves that K-stability of Fano varieties is equivalent to evaluative stability, a notion that he defined for Fano varieties, Q Fano varieties, and that's a nice work because it allowed us. Well, it gives a nice tool to the moduli space of K-stable Fano varieties, and this was used very very fruitfully in the last few years. So with Rui, we wanted to know if we would be able to define evaluative stability and prove that or something, or to understand that its relation with K-stability. And we succeeded in this. We are, well, I think, at least I am very happy with our results, but we also found very strong evidence that this notion of evaluative stability is not equivalent to K-stability for generalized polarized varieties. So this is what I want to explain today, or the definition of evaluative stability and its relation to K-stability. So there's two notions. So there's the notion, like I said, Fujita was working on Q Fano varieties, and he proves that K-stability, that in this setting, K-stability corresponds, maybe I should say one-to-one, to evaluative stability. So the first part of my talk would be just to describe these two notions, K-stability and evaluative stability, maybe in more easy way. So like any notion of stability in algebraic geometry, there's a geometric or algebraic data and some numerical invariant attached to it. Okay. And being stable is exactly that this numerical invariant is positive, or well, there's also some subtle notions of semi-stability and uniform stability, but I will be very basic about this. I would just talk about stability, or well, let's say semi-stability. So we're meaning that the numerical invariant is non-negative. Or is non-negative, yes. Okay. Okay, to describe the K-stability, I first did describe the geometrical or algebraic data attached to it. It's given by polarized variety. So maybe I should say that this notion has been developed by Tian, by Donaldson, and also many other people over the years. And I described just a very simple part of it. So there's a C-star action acting actually, this is a C-star linearized action. So it acts on the total space of L, if you want. And there's a map from the total space curly X to P1 that I consider as the compactification of C. And for T in P1, I denote xt, the level set of pi at T, and LT is the restriction of the line bundle to xt. And the condition, actually there are some conditions, but I will just name well, the more important, but the one I will use in this talk is that xt lt is is isomorphic as a polarized variety to xl if t is not 0, and also x0 as 0. So this is the pre-image, well, the polarized variety associated to a not necessarily polarized variety, but this is well, let's say that x0 is the pre-image of 0 by the test configuration map. And maybe I should have said that L, well, more generally, well, I will assume L ample, but actually it's L is just semi-ample or relatively ample. And more generally, okay. And so that thing is the central fiber, the pre-image. Okay. And numerical invariant attached to it is what is called the Donaldson-Fideki invariant. This is morally the classical Fideki invariant of the central fiber with the action. So here we have an action C star on the space of section over the and I will put here K, the space of section over the central fiber, and the numerical invariant will be essentially the asymptotic well sign, let's say, of the weight. So more precisely, if dk is the dimension of that space of section, and wk is the weight of C star on that space of section still, then we have an expansion. Well, let's say this way, F1K, and then the Donaldson-Fideki invariant of the test configuration is minus 2F1. So maybe we can discuss about the sign or the sign or the 2, but well, it's just the idea that matters here. Okay, so we have this for the case stability, and the evaluative stability. Actually, it will be dependent on a valuation. This is my valuation name. Okay, so we will have F, a divisorial valuation. Okay, so you can think about F as a prime divisor that lives into another variety, and there's a birational map from Y to X. Okay, and we will ask, well, a condition on that divisional valuation. We will ask F to be dreamy. So so this is this condition is a finite generate. The condition is like some filtration is finitely generated, and I will give the definition a little bit later. And we will, so with this dreaminess condition, we will be able, actually, as you will see, to construct the test configuration. That will come, the correspondence will come from that. And with that, we have a numerical invariant. So the numerical invariant we have, so it depends on L, but I will probably forget the L and the notation very soon. And this is given by the log discrepancy of F on X times the volume of L plus another term, which is N. So N, I didn't say, but this is the dimension of X, the dimension, I assume that the variety has, times mu. I will define what mu is very soon. 0 plus the integral from 0 to plus infinity of the volume of L minus xf dx. And the third term, which actually doesn't appear in the Fujita definition of invariant in this setting, is the derivative of the volume of that divisor along the canonical divisor. Okay, so here it's x. Sorry. Okay, so here, as I said, so here this is the log discrepancy. So mu is just an intersection number minus kx with ln minus 1 divided by ln. And here, this is the derivative along t of the volume of L minus xf plus t kx at t equal to 0. Okay, so this is the data we have.
Eveline, what's the coefficient in front of the first integral? It's mu and n mu?
This is n. So you mean the first integral here, it's
okay.
n? This is the dimension.
Okay,
Sorry.
but I think I should be minus, no? Somewhere.
The dimension of x. So you think I made there's a typo in my notes, maybe, actually. Maybe there's a typo. I really, for the precise signs and formula, it's better to look in the paper than in my talk. Sorry for this. Okay. Okay, so this is the all the data needed to define. And so in the case where L is the anti-canonical bundle, then Fujita has proved, so first, actually, this second volatile stability with the divisor and everything, this was all developed in the case of Fano varieties by Fujita. Okay, so this invariant was not the same. It was simplified, probably without typos, but so it was the beta invariant of Fujita. But all this notion of idea of looking for a dreamy divisor and building a test configuration out of it, it's really Fujita's idea. And so but it was working in this setting. Okay, assuming that L is the anti-canonical bundle, and then in this case, the invariant he got. So sorry, maybe I would take more space for this, and then the beta invariant he had was AXF. So the log discrepancy again. Volume of minus kx minus 0 plus infinity of the volume of minus kx minus xf dx. Okay, and in this situation, it proves that a Q Fano variety is k-stable if it's relatively stable. Okay, with all the precise notion like semi-stable, uniformly stable, and stuff. But just like loosely speaking, this is what he proved. So this is so there is one another result that I think is important to mention now. And this is a very big and useful and important result due to Li and Xu, where they prove that the Q Fano varieties are k-stable if and only if they are k-stable with respect to test configuration actually that are spatial with respect to spatial. Well, this is very specific way of saying a spatial test configuration, which implies that the central fiber is reduced and irreducible. This is actually says that this is integral. Okay. Integral variety. So it means that if you want to check if Fano variety is k-stable, it is sufficient to look at all the test configuration that have a reduced and irreducible central fiber. Well, this is probably not true for a more general variety, and so it's not surprising that that relative stability is not enough to check a k-stability. So what we proved with Rui is that if we have a polarized variety, so here I'm assuming that the anticanonical line bundle is Q-Cartier. This is necessary to define the log discrepancy, well, the way we use it at least. And so we prove that polarized variety XL is relatively stable if and only if it is k-stable with respect to integral test configuration. So what we mean by that is test configuration with such that the central fiber is integral, that is reduced and irreducible. So well, it's not completely crazy that this condition of integrability comes in at some point, because evaluation, the way we use it and the original meaning, actually only makes sense for integral variety. So it was not completely, well, surprising. Well, that we get this. Okay, and so as I said, I don't think that relative stability is equivalent to k-stability, and the reason why is that actually, so we have one example in the toric setting where the toric variety is k unstable. But actually, if we look only at the divisorial valuation that are invariant by the torus, then it is relatively stable. So in some sense, this is weakly equivalently stable, but not k stable. So maybe I can be more precise with this. So in the toric case, if we have a polarized toric variety, we could say that a divisor over X, well, maybe I should be more precise here. So what I mean is divisorial valuation. Well, you can say divisor over X is toric if its center in X is invariant by the torus action. Okay, so you can imagine that you have it corresponds to one actually, so it corresponds to an element in the Lie algebra of the torus, if you want, or in Q in the yes, you can think about it this way. And so if we look only at these toric divisor, then it is a semi-stable, relatively stable, if and only if the classical theta key invariant is 0. So in the toric setting, the classical theta key invariant corresponds to barycenter. Actually, the difference between the barycenter of the polytope corresponding to the line bundle L, the ample line bundle L, and the boundary barycenter. And so, so the reason why we think then that that relative stability is not enough, or at least equivalent stability is not enough, is an example from due to Donaldson of a surface, actually a toric surface, XL, such that the classical theta key invariant is 0, but actually XL is unstable, is K unstable. Okay. So of course, that's a counterexample that relative stability is equivalent to or not equivalent to K stability in general, but that's strongly that's a strong evidence that it won't be. Okay. Okay. So about what I want to explain today in this talk. So there's two parts of the rest of my talk. Let's say the first one will be showing that the divisional valuation can be made can really put in a correspondence with integral test configuration. So we'll have a one-to-one correspondence between. Actually, here I'm lying. It's not exactly that. It's dreamy ones. Dreamy divisional valuation are in one-to-one correspondence with test configuration. So I don't know if I will have time to go to show that the numerical invariant, so the Donaldson theta key invariant of that test configuration coincide with the beta L invariant of the dreamy divisional valuation. But well, let me say that it's not, well, it's not so easy. It's not just like computing the two invariants and seeing that they are the same. It needs some work, and a very non-trivial tool we use to prove that the numerical invariance match is the scaled MMP, which is due to sorry, I don't want to due to Kalogiras. Sorry, I'm certainly not pronouncing right. Kuronia and Lasik in 2010. And also so this is one of the tools we use, and also the asymptotic Riemann-Roch formula of Fujita. Okay. But well, apart from that, it was very for the way where we had to prove some technical stuff to show that it worked, but we essentially followed Fujita's lead for this. Okay, so let's start. So the correspondence between dreamy divisional valuation and integral test configuration it's going to be through a filtration. Okay, so but let's first define what's a dreamy divisor. So so again, I have depolarized a variety of dimension n that I assume normal and irreducible, and f is a divisional valuation. Okay, so we would say that f is L dreamy. I will forget about the L, just like it depends on L, but f is L dreamy if the Z2 grade C algebra that one is finitely generated for some fixed R. Okay, so what does that mean is that we have, again, a birational map from Y to X and F, a prime divisor in Y. Okay, and so for K in Z greater than 0, X will be always a positive in here. And then we consider the following. So this is a vector space that I will define. Sorry, F. So actually, so it's going to be the space of a section over Y into the pullback with value in the pullback of that line bundle. Actually, that vanish up to the positive integer smaller than X along F, okay? And so really, this has to be understood as a subset of section over Y into the pullback of the line bundle, vanishing along F up to some order, okay? And actually, this is then a subset of L, of a section in KL. So given divisional evaluation, we consider some filtration of that space. Okay, and so the fact, so the condition to be dreamy, so F dreamy, means actually that the filtration we have is actually well, over K is a finitely generated filtration. A finitely generated filtration. Okay, and of course, of that algebra, of the homogeneous coordinate space. Okay, and so what we do with such a filtration? So typically, we can produce another variety. We take the relative proj of that graded algebra, okay, and this is a relative proj, so we get a test configuration with a relatively ample line bundle, okay. So given F dreamy, we can build a test configuration over XL simply this way. Now to get further, we need to we will see that to associate the visual evaluation, we will use a one-to-one correspondence between test configuration over XL and finitely generated filtration of that space, which is due to David Wittgenstein and Gabor-Skaed, and two separate papers that come put together gives this correspondence. Okay, so here, so the filtration. So maybe I can write this space RK, and the filtration, if you want to see it a bit more geometrically, you can define it this way. So the subspace given by the filtration will be the space of section over the test configuration with the section in K. So you have a decomposition into weight space. Weight space decomposition and then you restrict to x1, which actually corresponds to x. Okay. So this is one way to define the filtration that makes it maybe a little bit more geometric. Okay. So yeah, so maybe it's not obvious from the definition that the test configuration we get is integral. And but actually the proof that it is very easy. So and it's essentially to Fujita, we essentially just realized that actually it was working very easily on the same way in our case is and I think it's an enlightening well, it's simple and very enlightening. So I will do that. So let's just make the proof of that. So because we take the relative Praj to construct the test configuration, we know that the coordinate, homogeneous coordinate ring of the central fiber will be given by this. So the central fiber, oh, I didn't denote central fiber this way. So let me be more precise. So it's going to be the sum over some numbers, lambda, f lambda, r, k, quotiented by f lambda, r, k. So here it's lambda plus 1 and r, k. Okay. So in our case, if we look at the space, f lambda, r, k, quotiented by f lambda plus 1, r, k, if we take off 0, it's going to be exactly the sections of LK vanishing exactly lambda time along F. Okay. And so this is crucial in the proof. So let's call this space SK lambda. Then to prove that that the essential fiber is reduced, so what we need to prove is that its string of section is an integral okay, and so this means that if we have a section in SK lambda and another one in SM, let's say mu, then the product lambda times mu, or maybe I should take that off because it's doesn't help. Lambda times sigma times tau is going to be a section, of course, is going to be a section of L, K plus M, but also if you look at its order of vanishing along F, it has no choice to be exactly lambda plus mu, okay? And so in particular, sigma times tau is not 0, okay? So it's very simple, but it gives, I think, a good idea why it works. And so the converse is not so easy, but still it can be done very in details, I think. So if you have an integral test configuration, now we want to found some dreamy divisional evaluation somewhere, okay? And so assuming that X is an integral test configuration, we will need to take some resolution of X because we want to use Buxom Hisamoto Janssen theory, which works for test configuration that dominates the product. So we take a resolution Y, P and Q, and then we consider, so if X0 was the the test configuration, the central fiber in our integral test configuration, then we can take x dot at the strict transform of x0 in y, and we compute. So with this, we will, well, maybe this is not so necessary. So with this setting, so I actually, what x at will be here, it's gonna be one divisor in the one prime divisor in the central fiber of y, and as such, Buxom, Hisamoto, and Johnson proved that such a divisor was actually defining a divisional valuation on x. Okay, and this is not so well, this is not obvious, because even if x0 is, so maybe I can write some things. So x0 is a prime divisor in y, but that doesn't mean but y is not birational to x. So something has to be proved, and this was proved by Buxom, Isamoto, and Janssen. So they proved that if you define that thing, so if you pick a section of LK over X, and then you take its pullback to Y. So remember that Q was the map from Y to X times P1. Then actually it defines a divisional valuation. Actually, so Buxom, Hisamoto, and Hansen were working in a more general setting, for a more general test configuration. But in the case we heard, we can use it this way. And here the associated filtration, because with respect to a test configuration with a valuation, you will have a divisional valuation, you have a filtration. It's going to be this way, and then M. So here M is the order of vanishing along x0 at of the Cartier divisor. Oops, there's too many. Here it's P, Q, L. Okay, defined this way. Okay, so what we have with this, so here maybe if we write it another way, it's going to be H0x and KLK minus X V0, the divisorial valuation here. So here that corresponds to the prime divisor F, if you want. And X is that thing. So yes. So X is Km minus lambda. Okay, and so using their theory, we get that given an integral test configuration, we have a divisional valuation, which actually has to be dreamy, because the filtration we get is the filtration associated to the test configuration, and so it is finitely generated. So it's going to be dreamy as well. And so maybe just to conclude that, so that is like an integral test configuration leads to a divisional dreamy divisorial valuation. Okay. Okay, so very good. So I think I will have time to talk about the numerical invariants. Okay. Okay, so what about the numerical invariants? So maybe some definition first. So The pseudo-effective threshold, tau, is defined this way. And as I defined before, dk is the dimension of the space of section over the central fiber. And wk is the weight of the C star action on that line. Okay. So we will use a proposition by Wittney-Strom, CKD, and well, it's been refined by Buxom, Isamoto, Janssen. Is that if f lambda is the filtration associated to the test configuration, then actually the weight is expressed this way, can be expressed this way. Okay. And dk is the sum over lambda of the dimension of that thing. So actually, so this is this really comes from the Rees construction I was talking about just before, you know, because sorry, oops. So because we have this actually that we have all this this representation. Okay, so this is, well, this is a proposition, but this is not so complicated. Maybe what is not clear in what I was just saying, so maybe I can take that off. So is so here lambda runs into runs in a finite number that depends on k, lambda min to lambda max k. Okay, and so we might need to rescale L to be sure that everything works fine. But if we do, like rescaling if necessary, so add some well, like for k big enough, we will have lambda k min or max being k times lambda min, lambda max. Okay, and then with this we can prove that that in the setting above, that we get that that actually so that implies that our that the filtration is linearly bounded, and actually linearly bounded by the constant. We actually the constants, the rescale constant, are given by 0 and the pseudo-effective threshold. Okay. So we see that as the log, the pseudo-effective threshold actually is the bound, the number at which this divisor stop being big. Okay, so after tau, the volume of that thing will be 0, and so it doesn't really come into the picture when you compute the integral of the volume in the beta invariant. Okay. Okay, so maybe something which could be good to notice is that actually this weight is a telescopic sum, and so and thus we will be able to write it as WK. So the weight will be minus k tau f. So here, of course, there's this L, but I don't really, because it's Vex, we don't really care. And then the dimension of RK plus some function FK that has been studied by Fujita, and actually we will be able to express it this way. So where again Fk is equal to the sum with lambda greater than or equal to 1 of dimension of of f lambda r k. Okay. And so actually here using a theorem, actually theorem 3.1 in the Buxom Hisamoto Jansson paper, we can say that this is this has the following expansion: fn plus 1 k n plus 1 plus fn k n plus o k n minus 1. Well, as I said before, this part was well, nothing changed in the case of polarized variety. Really, Fujita that was already there. So the fact that the theta k invariant is not the beta invariant is not the same came after. Actually, what we have, what one can prove, is that the Donaldson theta k of the Donaldson theta k of the test configuration that we have out of the divergent evaluation, it can be expressed with these, with respect to these coefficient fn and fn plus 1. Okay, and so for the rest of the proof is to be able to express these coefficients in terms of the volume of some divisor, and for this we need to some kind of Riemann-Roch theorem. Okay, so just as recall, so these coefficients will appear as the sum of some dimension of weight space. Actually, this is the way we should express it this way. Okay, so this is the dimension of a weight of a weight space, and this is how the Riemann-Roch or equivariant Riemann-Roch could come in. Okay, so maybe before going to the complicated part of the proof, just a remark. So when x is smaller than tau f, so it means that x is in 0 tau, what we know is that L minus xf is big, but not necessarily ample. Okay, so for example, of course, at x equals to 0, it's going to be ample if we started with an ample line bundle, of course. So imagine if it's completely false. Imagine that L minus xf is ample for all x in 0 to tau. Okay, in general, it's not true. But if it's true, okay, then you can use directly the Fujita's variant of the Riemann-Roch theorem, okay, to prove the following. Okay, to prove that the n plus 1, so maybe here I should write it correctly. This is n plus 1. To write it this way, okay, as the integral over the 0 to tau of this intersection formula. Okay, and then if we assume that we can do that, then you can replace ky. So in the setting we have a divisional evaluation. We have a y, which is a normal variety birational to x, and then we can replace the divisor, the canonical divisor of y plus f, as a pullback of kx plus the log discrepancy of f in x times f. this is the definition of the log discrepancy. Okay, so if we replace that, then we use some integration by part, which is not so easy. It was not so hard. Sorry, not so hard. Integration by parts is not so hard. And then we have that the Donaldson-Wittek invariant of the test configuration we build is actually beta f. Okay, just like replacing that. Okay. And actually, to be completely honest, this is how we found a beta. Okay, we did that and we found beta. Now it's another thing which makes it just a bit more difficult is that actually we cannot. So this is not true. Actually, this is never true. Essentially, never true that L minus XF is ample. Okay, and this is where we need to take the big tool of MMP, what we as Fujita did for in a setting. Okay, so this is the big theorem that well, personally I used as a black box. I don't really know how to prove that thing, but I was happy that we were able to use it. So there exists a sequence. So so what you do is that you break the little segments you have. You build it in a partition. Actually, you have a partition of this, and birational contraction. Okay, where all these Yj are projective normal varieties, okay, and such that actually even if that one, so this is a contraction, so even if this one is not ample at some x, then actually the push forward will be ample. Okay, and this is what we use, and also what happens on the boundaries, that it becomes just semi-ample. And the other part we used very much is actually we have this, of course. Okay, and so so we can use that. So maybe I should add everything I know. And semi-ample for tau g minus 1 tau j. Okay. And so what we were able to do with that we were able to manage the term of these coefficient fn plus 1 as follow: j equal to 1 to m. So m is the number. I don't know if you see enough. So m is the number of partition you have. We need 1 over n factorial from tau j minus 1 to tau j lj minus x fj dx. So I think I forgot to define lj. So lj would just be pi star L. So here that's going to be the pullback of L, right? And Fj will be again push forward by J of F. Okay. J and F and will be minus sum J 1 to M 1 over 2n plus 1 tau j minus 1 tau j Lj minus xfj kyj plus fj dx. Okay. And then with this, or here, I think I forgot n, and here probably n minus 1. Oh, and here it's n minus 1, 2. Okay, and this is so this is with this that we are able to found. So maybe another comment here is that, of course, we use the fact that that thing is ample. Then we can use that this thing is the volume of Lj minus xfj. Okay. And so and then we're good because we're just we have a partition of the segment, and then we have the volume. So a numerical function, it's a function on each part of the partition from 0 to tau, and so we can just, of course, well, put the integral together. Okay, thanks a lot for your attention.
Yeah, thank you very much. So we have like maybe 2-3 minutes for questions.
So it seems that your evaluative stability is defined only for dreamy dividers, right?
Yes, but yeah, a priori, yes.
But is it equivalent to? But from the formula, it's obvious that it can be defined for any prime divisor over X. I mean,
yes.
So is it equivalent between the two definitions? I mean, for dreamy divisor and for any prime divisor, just like Cantor Fujita?
I don't know, but I think that's an interesting question. Personally, I don't know.
Okay, thanks.
I have a small question. Basically, when you define beta invariant, first you define it in the way you put in your lecture. But then you basically rewrite it in slightly different way. So which is clear that is generalization of Kenta beta invariant. Why you didn't define it in this way from the beginning?
You mean you mean not in my talk, but in the paper, you mean?
Yeah.
Yes, actually, I think it's interesting to see the well, to see the derivative coming in.
I see. Okay.
I think it's but of some sense, like when we're in the proof, like if you want the history of the proof, then we compute the Donaldson Fitaki invariant and of the divisorial, well, of the Fitaki of the test configuration we have, and we could have just defined it this way, and then we have the formula you mentioned about with this intersection formula, intersection numbers. But actually rewriting it with with the derivative of the volume seemed interesting for us, but we have indeed the two ways.
And another question, so you said that you expect that basically evaluative stability is going to be very different from case stability for general polarization. Yeah?
Well, very different. I don't know.
Also different.
But
yeah.
different. I think that so like for example so of course, when we can manage just to check special test configuration or test configuration with reduced and irreducible central fiber, like it's the case for some spherical varieties, then which are not necessarily Fano, like for polarization that are not Fano but are close to, like Thibaut Delcroix proved recently, then it's going to be enough. But in some sense, like if it's equivalent, that means in some sense that it's not equivalent to equivariant stability, because the example we show. Well, that would be okay, but or maybe it's not the right way to define equivariant stability. Or well, I'm very open, but I don't. Well, personally, I would be very surprised that it's equivalent.
But do you have some condition on polarization which basically tells you that evaluative criterion guarantees k-stability?
Like for some polarization, like for example, in our paper we have yes, like in terms of some kind of delta invariant or things like that. That what you mean? Or
maybe some numerical condition on polarization, something like easy to check.
Well,
close to Fana or something like this.
Close to what? Sorry.
Fana.
Close to Fana. Well, I don't. Apart from the thing we have in our paper on delta invariant, I don't. And these are very specific examples. Like, but no, not that I know.
Okay, thank you.
Okay.
I also have a question.
Technically over time, so if there are no more questions, maybe I will close it.
Wait.
Okay.
Florian wants to ask a question, I think. Wait. Florian, do you want to ask a question? Yeah.
So you fix this valuation, and then you have to know the entire function. I mean, from 0 to this how do you call it, pseudo effective threshold, right?
Yes, 0.
This volume function, right?
Yes.
So my question is, you define all this invariance in terms of the knowledge of the whole interval, right? So my question is, if you only know this function from tau minus epsilon to tau, where epsilon is small enough, can you still decide from this information stability with respect to that valuation or not? Or
that's interesting. I never thought about that, so I cannot answer you. But so the idea would be like you know that volume function here, and then you wonder if you can know everything about it. If it's not everything about it, but that you know if it's stable or not.
To decide stability or not, yes.
Yeah, I don't know.
Really know the whole interval, or
so I don't know. I did never ask that to my. I don't know, but I think it's interesting in the sense like if you look, because we are looking at the derivative of the volume, and so this is where things could go wrong. So I agree that it's a good question, but I'm sorry, I don't know what to answer.
Okay, thank you.
Okay, thank you.
Any other questions? No? Well, thank you very much, Eveline. It was quite entertaining. See you all next week. No, next Thursday.
Bye, thank you.
Bye, thank you.
Thank you.